dot head as close as possible to the W and W dot. So likely, we want to have the observer pulse as close as possible to the zero. Okay? If you cannot get the dead B, then we wish we can have as close as possible to the dead B. All right. Now, in a common filter, what do you mean common filter? Common filter means under the noise assumption, there's a noise is input noise and measurement noise, then that means this equal to like what we call optimum observer. That means this is we call as close as possible to the dB. That's the best you can do. Okay? The common filter observer, the common filter, the observer pole will be the pole that you can get. You cannot get better than that. That's what they call observer. But what I'm showing you is the analytical model, so we don't have such problem. We assume that everything is perfect, so I can get that B. So in the power placement technique here, your system model, you need to move your pole from open loop pole to the closed loop pole. In the observer, we also move the pole from your open loop pole to the observer pole. So you have two kind of pole. One is closed loop pole, one is observer pole. Now, we like observer poles always better than closed loop pole. The better means the close to the zero. Now, you might think, say, how about, can I have my closed loop system become a dead B control? Right? That's a good question too, right? Can I have a dead B control? Dead B control means I will control my system such that my closed loop eigenvalues are all zero. That's good too, right? That means my observer pole are zero, eigenvalue are zero, my closed loop system pole also zero. That would be perfect. But observer is easy to do if we don't have noise. But how about closed loop pole? How about can we do that? That's good questions. Well, in theory you could. If you have your control device can provide you the power you need. Right? You are a trader. May not be able to provide you the power that's large enough to get that B. You might have a lot of force to get that B. And that may not be possible because of your control device. But observer, you don't need the power. You need just only measure. So, the observer, there's no problem to get the dead B observer. The only problem observer, you cannot get dead B observer is because of noises. uncertainties that avoid you to get the debit observer. All right. So from this case, we can see that our system cross-loop eigenvalues are not zeros, but our observer poles are zeros. Right? So here, you have to be very, very careful about this, the control. Here we have observer poles, and we have cross loop system poles. All right. In our example, this is all zeros, and this not zeros, right? That means my observer poles are faster than the cross-loop pole. I mean faster. I call faster. I don't call better. I call faster. Meaning they converge to the true state very faster. Then my cross-loop pole control my system to the zero states. So that is my example here. Now, if on the other hand, if I say my observer poles are smaller than closed-loop system pole, then what happens? Can anybody answer that question? If my observer poles is smaller than the closed system poles, means my closed-loop system pole are more stable than my observer. And what's going to happen like that? In general, the observer poles are more stable than closed-loop pole. Means this is pole closer to the zero than closed-loop pole, and then that's what happened there. If, on the other hand, if my closed-loop pole poles are more stable than the observer poles. Okay. Then what happens? Then what happens? Then what happens? Think about it. My estimate state, they may not be converged to the true state faster than your closed-loop pole. That you are using, that is not really the state you got to go closed-loop pole. it's getting the closed loop system response. It won't become unstable, but will be very slow and stable. Okay? In theory, I'm talking about in theory. In practice, it may become unstable. I say in practice, because in practice means what? Means your observer are not really good because your measurement noises and system noises are very high. So you cannot get the observer pause better than the closed loop system pause. For that case, you better tune your closed loop pause small. Don't be too aggressive for your feedback. That's what it means. All right? Be careful. When your measurement is very noisy, then you don't expect your closed loop will be very good. So your measurement devices are very important. Your measurement devices is very good, very clean, only with the minimum noises. Then you can get very good observer. If you get very good observer, then as long as you have very good controller devices, you have a good thruster, you have good actuators. So this depends on two things. One is sensors, one is actuators. Sensor has to be very good. Then your observer will be very good. If sensor is not good, very noisy, that means your observer won't be too good. Then it doesn't matter how good of your actuator is, sorry, you can expect to have a good closed loop system. Well, that's understandable, right?